Alrighty, guys. Good morning. Welcome back. Sorry for the delay there. Zoom insisted on running an update. But today the plan is for Daniel to share with us section 5.4 on indefinite integrals and the net change theorem. We've talked a little bit, and Daniel, I did see one email from you last night that I wasn't able to respond to in time. But I think we're in pretty good shape. Is there anything you would like to ask or discuss really quick before we get started?
I mean, there's only one thing that I don't know, but it's like really specific and it doesn't actually pertain to like the lesson. I guess it's just more like of an understanding question.
Okay, well, when we get there, just don't be shy about it. If anything
Yeah,
like that crops up and you want me to fill in a detail or anything like that, don't be shy at all. I'm happy to do it.
I'm asking you because I couldn't really find it. Like I can still teach it all, but I just don't understand that part. So, but hold on, just give me like 1 minute. I'm like organizing things right here.
Sure, of course. I'm going to go ahead and make you a co-host, which will give you the ability to screen share and do anything you need to do on that end. And if there's anything you need from me in the interim, just let me know. I'll go ahead and throw the title card up here so we have that at the start of the YouTube video. Okay. This is, of course, MAC2311. Section OH1, which is Calc 1 honors. And today is November 19th, 2021. Today, we're doing indefinite integrals. And the net change theorem.
Do you guys mind if I sit over here with my clock? Okay, I already know how to do this.
5.4, and this is Daniel's student teaching.
Yeah, exactly. And then for kinematics, actually for kinematics.
Oh, and I didn't mute anybody by default, so if you got something going on in the background, I may mute you there. But if you want to talk, of course, as always, just hold down the space bar, unmute yourself. And yeah, Daniel, just let me know when you're ready, bud.
Can you guys see anything?
So you are there now. I can spotlight you in the.
I don't know how it comes out. I mean, I can't see. Okay, there.
See.
Oh, look better.
I do think we'll need to rotate though.
Oh yeah. Or oh shoot, I didn't think about this.
It's all right. Take your time.
Okay, wait. Give me 1 second.
No stress, man. No stress.
Is that good?
Yeah, we got the right angle there.
Okay. I just don't want my phone to fall. It's sitting on a bunch of canned food.
I see that. Yeah, it'll work. It'll work.
Okay. Let me just I'm gonna write something. Does it look clear? I'll write it better next time, but
yeah, no, this works. Just continue writing nice and big like that, and I think everything will be just fine.
okay. Right, sounds good. So the lesson's indefinite integrals and net change. I'll just say I'm probably going to talk a lot more than I'm going to write. I'm going to try and write as much as I can, but if I like go over anything, just stop me because I really don't like writing. But I'm gonna write all the important things. Don't worry. But I'm not going to write everything I said. So I'll write the definition. So the definition of an indefinite integral, and I guess I kind of came up with this a little bit. And so what it does is it undoes a derivative. It is the antiderivative. It is the antiderivative. derivative of a function. Can you guys read that there, or does it need to be repeated?
I think probably everybody can hear you just fine. It is a little hard to read the text, but not impossible.
Okay. And something else about indefinite integrals is the answer is a function. The answer is not a number. Emphasis on not, because well, the indefinite integral, what it does is it's going to bring you back to the previous function. And so it's not a number. And if you get a number, you're wrong. But I'll show you a little bit what it means now. So let's say we have f of x, okay? If we take the derivative of f of x, we get f prime of x, okay? So by the definition, what was that? Okay, by the definition of what I said before, if we take the integral, indefinite integral, so there's no lower and upper bound. Forgot to say that before. No lower or upper bound. And that's a little hard to see there, but I said no lower or upper bound. But anyways, if we take the indefinite integral of f prime of x, what we should get is f of x. Now, this is true almost, but if we are not given f of x, let's say we start with f prime of x. If we start with f prime of x and we're told to find f of x, this is not going to be true here, because there's going to be plus c, where c is equal to a constant, an unknown constant. And this is because, let's say we have x squared plus 4, okay? And let's just say we have this. Stop focusing on this for now. If we take the derivative of x squared plus 4, it's going to be 2x plus 0. So we wind up with 2x. If we're told to take the integral of 2x, let's say we do not have this here, we do not have the x squared plus 4, we're not gonna know what this number is here, so we can't put a definitive number there. So we put plus c to represent it. So like if you're asked on a test to just find the integral of something, and you do the integration, which I'm going to show soon, you have to put a plus c at the end, because there's a number that you cannot find. You don't know if it's there or if it's not there. It could be, there's technically an infinite amount of possible answers that you could do, because you don't know what the number is that was there before. But if you're given it, then you can go back and forth. That's fine, but most of the time it's not the case. Okay, so now I'll show you how to do the derivative, or I mean the integral. Is that good? Yeah, it is.
Mm-hmm.
So let's say we're told to find the integral of x, just x. So if you recall, I said that the integral is the antiderivative, so you're going backwards. And if you also recall the power rule of derivative, you are subtracting the exponent by 1. And when you're doing the indefinite integral, the antiderivative, you're going to do the exact opposite, plus another step, which I'll show here. But the formula is going to be x to the n plus 1 over n plus 1, and then plus c. And can you guys read that there? I can repeat it. this is x raised to the power of n plus 1. And n is the current degree of whatever x is. So in this case, it's 1. So the integral of x is going to be x to the 1 plus 1 over 1 plus 1 plus c, which gives us x squared over 2 plus c. And to prove it, if we take the derivative of this here, x squared over 2 plus c, we're going to get 2x to the first power over 2. Can't 2's cancel out. We have x again. That's where we started. And the derivative of the constant is going to be 0. So it's plus 0 here. And then when we take the integral again, if we were to do that, we're not going to know what it is. So we have to put a plus c at the end.
Just one little note. So the
Yeah.
notation he's using here, the integral symbol without bounds, that is called the indefinite integral, right? That's the object of study today. We do still want to write a dx at the end, though. I know it might feel a little bit weird.
Yeah,
Because there's no like width, we're not talking about areas, but it's just a notation thing. We do still write the dx. So this is good. The integral of 1 dx is x squared over 2 plus c. And that's that most general antiderivative from Talia's lecture. It's the same idea. And that's why that formula, the x to the n plus 1 over n plus 1 plus c, is the same formula. So the indefinite integral is really saying the same thing as in Talia's lecture, find the most general antiderivative, right? Indefinite integral of some function is the most general antiderivative of that function. So it's essentially the same thing, just in a notation that's a little bit more evocative of what we've been doing with integrals in general. Yeah, beautiful, very nice.
Okay. Next, okay, so say if we have the integral of x to the third, well, it's going to be the same thing. We're going to use that. It's going to be x to the 3 plus 1 over 3 plus 1 plus c, which gives us x to the 4th over 4 plus c. And you take the derivative, it's going to give us 4x to the third over 4. 4 cancel out, gives us x to the third. And constant derivative is going to be 0. And that's basically how to do it if you just have a single variable. It's not going to be the case, pretty much never. But let's move on to slightly different problems then. So if we have the integral of the square root of, let's just say, x to the third. In this case, what you do is you recall that x to the third is equal to, just going to put the integral sign again, of x to the 3 over 2. And then from there, you're going to use the rule again, x to the n plus 1 over n plus 1 plus c. This is going to be x to the 3 halves plus 1 over 3 halves plus 1. And plus c. I will just put the plus c every time. If I don't, I usually forget to do it by the end. So that's a little note. But 3 halves plus 1, that's going to be 3 halves plus 2 over 2. It's going to give us 5 over 2. X to the 5 halves. And this is how, I don't know, I do divide fractions. You might do it slightly different, but I'm going to put x to the 5 halves over 2 over 1 because there's going to be a fraction in the bottom. And it's going to be the same thing here. There's going to be 5 halves in the bottom because 1 is equal to 2 over 2, common denominator. And then I'm going to multiply them. Maybe you do this slightly differently, but this is how I do it. So it's going to be 2x to the 5 halves over 5. And that's going to be the integral of x to the third, the square root of x to the third, I mean, which is also equal to the integral of x to the 3 over 2. And that's So you would do it with a square root. And by the way, going back to this here quickly, let's just say you have x to the third plus, I'll just do an example here quickly. But if you have the integral of any constant for whatever 100,000, you're just going to add an x. And that's, you can always trust that because I actually don't have a reason, but you can just add an x. Well, the derivative of 4x is 4, right? So the integral of 4 has to be 4x. That's what I'm using. And what was I going to say? Something important. Don't remember. Okay, so what if you have the integral, let's just say x squared plus 7 times x minus 7? Well, in this case, the best thing you can do is to FOIL it out and then take the integral. So this is going to be equal to the integral of x to the third minus 7x squared. Sorry for the bad hand. Plus 7x minus 49. And I forgot if this was shown in previous lesson in class, but to do this, you can just take it becomes the integral of x to the third. You can separate the integrals.
Very good.
The integral of negative 7x squared plus integral of 7x plus integral of negative 49. And something to note here is that when you have like negatives and numbers in there, you can move all of those outside of the integral, and then just take the integral of the variable, and then multiply it by that after. So let's say here we can move negative 7 out. Here we can move 7 out. And then here we can move the negative sign out. So negative 1. Just quickly look at correct. Yeah. Okay. So here we have the integral of x to the third plus negative 7 times the integral of x squared plus 7 times the integral of x plus negative 1 times the integral of 49. And we can take the integrals of all these separately, and it's going to be equal to the integral of x squared plus 7 to x minus 7. So integral of x to the third, and I'll write the formula over here again. Then plus 1 plus c. So integral of x to the third is going to be x to the 3 plus 1, so x to the 4th over 3 plus 1, which is going to be 4, plus the integral of x squared. So remember, let's do this here. Negative 7 times the integral of x third here, which is going to be x to the 3 plus 1. So x to the third over 3 plus 1, which is going to, over 2 plus 1, which is going to be 3. And then integral of 7 times x plus 7 times integral of x, which is just going to be x to the 1 plus 1, which is going to be x squared over 1 plus 1, which is going to be 2. Sorry, I kind of squeezed it all together. Might be hard to read. plus the integral of 49 and the integral of any constant. You can just rewrite it as the constant. Oh, I could have taken this out. I didn't notice that. This you can just take it out. But and the integral of any constant is going to be the constant times x. We can't forget we have the negative there. So it's going to be plus negative 49x. So it's going to be x to the fourth over 4 minus 7x to the third over 3 plus 7x squared over 2 minus 49x. And that's going to be the answer to this indefinite integral of x squared plus 7 times x minus 7.
If we're being picky, there's one little detail we want to add.
Yeah, it's a c.
Yeah.
That's what so you have to write it down or else you're going to forget like I just did.
Yep. And this is actually a good example to talk about something. So splitting up the integral, like Daniel did here, definitely the way to go, right? You integrate each of those individual power pieces on their own, but you don't need to write a separate plus c for each of them, right? If you look at his very top line there, we might think that each of these things should have their own plus c because each of them has their own integral. But really, there's no reason to do that. You can mash all of those together into a single plus c at the end. And I would recommend doing it exactly as he's done it here.
I mean, yeah, you could write plus c at the end, but at the end, all the c's are going to add up to just c. They're not going to accumulate on each other.
Yeah, if you put 5 arbitrary constants together, that's the same as 1 arbitrary constant.
Yeah, so it's just going to be plus c.
Yep, very good.
Make sure to write that or else you're going to forget it and you're not going to get full credit on the question.
Yeah, unfortunately, I do have to dink a little bit if we forget the plus c. I always hate doing it, but I always have to do it. So do be careful. An indefinite integral always gets a plus c.
Okay, so next one. Let's say we have, this is going to be a little different. Let's say we have the integral of 1 over x. So here, what we can do is here, you would, or I guess you, because you haven't done this lesson yet, but you could move the x to the top. This would become the integral of x to the negative 1, right? And then we can apply this rule here. It's going to be x to negative 1 plus 1 over negative 1 plus 1. And if you notice something here, this is going to be x to the 0 or 0, which is not defined. So you can't do this if you have 1 over something where the something on the bottom, the highest degree is 1. You can't do that. So what you have to know here, and this is just memory, but it's really simple. If you recall, when we're taking the derivative of ln of something, let's just say u, the derivative of ln of u is going to be u prime over u, where it's the top prime over the bottom. So the integral of 1 over x is just going to be ln of x. And this is because, if you remember, you look here, the derivative of ln of x is going to be x prime, which is 1 over x. So that's 1 over x there. And this is the same situation if you have the integral of 1 over x plus 10, for example. The integral is going to be ln of x plus 10. Because the derivative of the top, sorry, I didn't write derivative here. And this is going to be a plus t here too. But yeah, the derivative of ln of u is u prime over u. And so if we take this here, take the derivative of x is 1, derivative of 10 is 0, which is going to be the top 1 over the inside itself, which is going to be x plus 10. So that you're going to have to remember. And And that's how you would take the integral of something over something where the highest power is 1, in this case, x, or it could be another variable.
And I'll jump in just for a second here. The rule that Daniel's written down there, the ddx ln u equals u primed over u, this is actually hinting at a general rule for indefinite integrals like the one on the bottom there. So down the road, I will give you guys a very methodical way to evaluate the integral of 1 over x plus 10 by making a little substitution. So while this is certainly correct, and we can justify it by thinking about the derivative of the natural log of x plus 10, it's not something you're going to have to brute force memorize necessarily. You certainly do want to know that the integral of 1 over x is the natural log of x. Or if we're being very, very careful, the natural log of the absolute value of x. But down the road, once you have something more complicated like 1 over x plus 10, or 1 over any linear function, or even any ratio of polynomials where the degree of the top is 1 less than the degree of the bottom, you will be getting into natural logs there. And the way to do it is through something called u substitution, which is actually the very next section in the book. So you can kind of think of this as a little bit of a preview of what we'll be doing next. But it's not something you're going to have to necessarily memorize. We will have a procedure for it eventually.
Yeah, that's actually in one of the problems I'm going to go over soon, where if you're doing trig, you want to use u substitution. I'll show it briefly how you can do it without u substitution, but it's just pure memorization. So that kind of sucks. There is some stuff you're going to have to memorize for the integrals. You don't really have to quote unquote memorize it. It's just going backwards in the derivative. But I'll do that when we get there.
Cool.
So the next thing is we're going to do, let's just say we have the integral of e to the 2x. Now, there's also a formula for this, and that formula is going to be e to the cx. This is actually, I just made this up here, the c, but c stands for constant. Label that there. Constant, so whatever the constant is times x, and the constant can be 1. We're just not going to put it in. But it's going to be e to the cx over cx prime, the derivative of the exponent, and then plus c at the end. So that's going to be how you do the integral of e to the 2x, or e to the whatever. So here we would just copy it down the top, e to the 2x over cx, which is going to be 2x in this case, prime. The derivative of that is just going to be 2. And then plus c. What if we had the integral of e to the 2x squared? Well, we do the same thing. We copy this here. It would be e to the 2x squared over 2x squared prime, which is going to be 4x plus c. That's how you do it with the e there. And the next thing I'm going to go over now is what I was talking about before with trig functions. So let's say you have the integral, take the integral of sine of x, or yeah, sine of x. Now, if you just recall from memory, when we start taking derivatives, you take the derivative of sine, goes to cosine, right? Actually, no, I don't think this has wrong. Maybe it does. But if you remember the integral, the derivative of cosine of x, the negative cosine of x is sine of x. So the integral sine of x, that's going to be going backwards, antiderivative, is going to give us negative cosine of x. And that's, you're just going to have to memorize it like that. So if we have the integral cosine of x, if we recall, the derivative of sine of x is equal to cosine of x. So if you take the integral of cosine of x, you're going backwards, and we're going to end up with sine of x. And if you have, if the inside is not just x, the best way to do it is going to be through u substitution, which Professor Faustick will teach next class. I could show you here, but it's not going to make very much sense at all, and it's going to be just like very like menial memorization, and you're probably going to forget it really quickly. So I'm not going to go over that. But that's how you would do it with trig. You have to remember what derivative will give you this. If you, if say u substitution, which we're going to learn next class, didn't exist, we just have to recall taking the derivative of what gives me this, and then that would be the answer, and then plus c at the end. So the integral of this would be sine of x plus c. The integral of sine of x would be negative cosine of x plus c, because we don't know the constant, but we do know what the derivative before, meaning what comes, I guess, a little visual representation, what comes before the integral, or before this, would be sine of x. So that's how you do it with trig, but it's going to get a lot easier next class. So now we're going to be moving on from indefinite integrals to the net change theorem. Okay, so talking about the net change theorem, I'm going to talk about it a little bit in like a physics perspective, but I promise it's not going to be hard or anything. It's just like very superficial. It's just like the ways I'm going to represent things. So I'm not going to be doing like any real physics work. So if you recall from the fundamental theorem of calculus 2, not 1, the integral from a to b, and I'm going to talk about what I'm writing here after I write it in a better way, because I personally think sometimes the way these formulas are written, like kind of boring, and boring things are harder to understand because you don't want to pay attention. That's just me, at least. But so here we have stated the integral from a to b of f of x is equal to big F of b minus big F of a, which is also equal to big F of x evaluated at b and a. And basically what this means is here you're going to be, first maybe let me talk about what net change is. Sorry if I'm jumping a little bit over here, but net change. So net change means the net change. It's not just the change. So let's say I have a car in Gainesville for G, and I am going to Orlando for whatever reason. Oh, if I go to Orlando and then I come back, my net change is going to be 0 because I'm back exactly where I started. However, my distance is going to be whatever it is to Orlando. Let's just say 200 miles. I don't know if it's that or not, but my distance is going to be 200 miles and then times 2 again. And so the way that relates to this is in a problem, the way it's going to be given to you is, hold on one second, I'm trying to find the problem. Here it is. Okay. So the way it's going to be given to you in a problem is you're going to be given, let's say in this case, v of t. And this is where I'm going to be talking about it from like physics perspective a little bit. V of t means the velocity with respect to time. So you're going to be given an equation for v of t. And if you plug in t for whatever it is, minutes or seconds, you're going to get the velocity at that unit of time. And you're going to be told to find what, example, distance the car covered in whatever amount of time, let's say 20 minutes. And so what you're going to do is you're going to have to take the indefinite integral of v of t, and then the indefinite integral of v of t, and I'm just saying this here broadly, I'm not including any numbers or whatever. It's going to give you x of t, which is the position in relation to time. And I think that makes sense because the position in relation to time, it's like a graph here. Position, let's just say the position is this, you're moving at a constant speed, whatever. The derivative of the position time is going to give you the change in position, because the derivative is the change in something. So that's going to give you the change in position over time, which is the velocity function, which would be like miles per hour. Whereas the position function would just be miles. So here you're going to be taking the indefinite integral, and then you're going to evaluate the indefinite integral at the higher bound minus evaluated at the lower bound, which is exactly what this means here. And I'll ask Professor Falstiger the question that I didn't really understand about this.
Sure.
But let me do a practice problem here then for the net change theorem. So before we started, let me just say that example in physics, you have, this is generally how it is, you have x of t, position time, position over time, or position relative to time. You take the derivative, gives you velocity relative to time. And you take the derivative again, you get acceleration relative to time. I don't think acceleration is not really relative here. I'm just saying that there. But take the derivative, you get velocity. Take the derivative, you get acceleration. You go backwards, you get velocity, and then position. But anyways, let's say you have a car drives from Orlando to Gainesville. And the car's velocity is given by v of t, where v of t equals 50 plus 5x minus x squared. And I'm not saying this is any realistic function for the velocity of a car. I just came up with this for this. So the car, actually, let's make it positive so it doesn't go down. But
And one little note, we probably want to use t's, right? Instead of x's.
yes, that is true. I do this constantly on homework and stuff.
That's all right.
5t plus t squared. Okay.
Very good.
So that's where the velocity function is given by that. And you're going to be asked, what distance does it cover in, let's say, 10 minutes? And let's say t is going to be equal to minutes, not seconds, minutes. So you're going to be given this v of t function. And if you look up here, recall that velocity with relative to time. If you take the antiderivative of that, you're going to get position relative to time. And then from there, you're going to evaluate x of t, which let's say in this case equals f of x, big F. Big F of x equals x of t. And v of t equals little f of x. Sorry, I wrote this flipped here, but v of t is going to be equal to little f of x. You take the derivative of that, I mean the integral, and we're going to get big F of x, which is also equal to x of t, which is position. And so let's seek the integral. So we're going to have the integral of 50 plus 5t plus t squared dt. So remember, we can split it up. Integral of 50 plus, and we can move this out of the integral. So it'll be 5 times the integral of t plus the integral t squared. So this is simply going to give us 50t plus 5 times t. Let me write this here again. X to the n plus 1, n plus 1 plus c. And so it's going to give us t to the 1 plus 1 over 1 plus 1, which is going to be t squared over 2 plus t to the 2 plus 1, which is going to be t to the third over 2 plus 1, 3. And there's going to, this is my question here. Is let's do the problem first, and I'll ask the question after. But so we have this here. We'll just rewrite it here. 50t plus 5t squared over 2 plus t to the third over 3. And then plus c. And so now this is equal to the position time graph. We started out with the v of t here, velocity. You're given that, and we're told to find what distances it cover in 10 minutes. Now, we could go plugging in all the values and figure it out, but that's really menial, and there's a much easier way to do it. And that's taking the antiderivative, aka the indefinite integral v of t, which is going to give you x of t, which is position. And then you plug in 10. We're going to plug in, oh no, we're going to evaluate it at the lower bound and upper bound, b and a, which in this case is going to be 10 and 0. So we're going to evaluate this at 10 and 0. And just ignore this here. I don't think that would make sense if I put it like this here. But we're going to take the upper bound and subtract from the lower bound. Lower bound is going to be 0, so we're not going to worry about that. Let me just copy it quickly. So we have this here. So it's going to be 50 times 10. Sorry, this is a big number. probably should have taken that into account. We're gonna plug in 10 here. 50 times 10 plus 5 times 10 squared divided by 2 plus 10 to the third plus 3. And you can tell here, this is not going to be any reasonable distance a car could cover, like in a long time. And once you do this, I'll do it quickly just for the problem's sake. 50 times 10 plus 5 times 10 plus 5 times 10 squared divided by 2 plus 10 to the third divided by 3. And so the car is going to have cover. I actually didn't specify, I should have said what distance in miles or distance.
Yeah, we do have to be a little careful about the units. So if the time is being measured in, what did we say, minutes?
Yeah, it's minutes.
Have we specified the units of the velocity? So the velocity is going to be like distance over time. So if it's miles per minute or feet per minute, then the answer here would be in miles or feet.
Yeah, I should specify that. But since t is minutes and the distance is miles, which I didn't say before, my fault. And velocity is equal to distance over time. It's going to be miles per minute.
Yeah. So we're hauling some serious ass here. We
Sorry.
go quick. No, it's okay. It's okay. It works.
Miles per minute there.
Yep. So then our distance would be measured in miles.
Yeah. And so this is x of t. So this is going to be x of 10. Plug in 10 for t is equal to this, which is equal to what I plugged in there, which is going to be 1083.33 heating miles. And my question for you is, I couldn't find it, but why we like ignore the C here?
Yeah, well, it's actually up to you, right? So you can write the plus C there if you want, and then when you evaluate, you're going to get a C minus C, which will go away. But I think the more traditional thing is if we're doing a definite integral to leave the C off.
Oh yeah, because this is
Did we set it up as a definite integral, right? I think maybe maybe we kind of went back and forth a little bit. But when you evaluate, when you plug in the 10, you'll have a plus C at the end of that. And then we subtract off what we get when we plug in 0, which will have a plus C as well. So the C's will cancel, they will go away. It's not harmful to have it there. It's just extra writing.
yeah, when you're doing a net change theorem problem like this, it's kind of like we have to take the indefinite integral and then you evaluate it. So it is kind of like a definite integral in a way.
Mhm.
But and then if you guys would like, I will do another problem. I'll just do it. So let's just say water flows out of a hose at a rate f of t, where I'm calling this flow. Coincidence is f, but and f of t equals 5 plus 16x. And you're asked how much water flows, or let's just say leaves the hose in 45 minutes. And t here again is going to be in minutes. And I should have included this here. How much water is going to be in gallons? So your unit there is going to be gallons per minute, which is the what you're given here. That's the flow rate. So this is going to give you gallons per minute. 15T. Anytime T. Sorry about that. So you plug in 30, you'll get the flow rate at 30 minutes. And this is a linear function, so it makes a little bit more sense. Like the hose accelerating over time. The flow rate's not going exponentially or anything like the car from the previous example. But so if we take the integral of little f of t, which is going to be flow relative to time, this is going to be the integral of 5 plus 16t dt. And that's going to give us, you take the integral of 5, any constant, you can just add an x, or in this case a t. And then 16t, I'm going to take the integral of that, just write it out here just so you remember, but 5 is just going to become 5t. And then plus the integral of 16 times t. And so that's going to be 5t plus t to the 1 plus 1, right here again, n plus 1, n plus 1, and we're going to leave out the c, like Professor Foster said, because it's like we're evaluating the integral. So it's going to be plus t squared over 2. Well, we are going to keep this part. We do have to take the integral still. So this is going to be 5t plus t squared over 2. And that's going to be the total water that comes out relative to time. So let's just call that big F T. And I don't know if you guys can you can kind of see both pages here, right?
Mm-hmm.
Okay. I'm going to rewrite it here. F of t, big F of t equals 5t plus t squared over 2. And that's the total flow. And that's what we're looking for. We're looking for how much water in total in gallons leaves the hose in 45 minutes. And so we're going to have to evaluate this at 45 and 0. And 0 is just going to make this 0. So we can use that out. And we're going to evaluate it at time equals 45. So 5 times 45 plus 45 squared over 2. But I will write it here just for the concept's sake. It's going to be this for evaluating at the lower and the upper bound. It's going to be the upper bound, which is at 45, minus 5 times t equals 0, which would be 5 times 0, plus 0 squared over 2. And this is just going to be equal to 0. But 5 times 45, 5 times 45 plus 45 squared divided by 2. It's going to give us 1,237.5 gallons. And that's going to be in total how much water left the hose in 45 minutes, according to, we're given that this is the function for the flow rate. Take the integral of the flow rate, and then we get the total water that is left. If we took the derivative of the flow rate, you get the change in the flow rate with respect to time. Take the integral of that, you get back to this, and then you take the integral of this again, you get back to the total water. And that's going to be how you do that. And you evaluate it at the upper minus the lower bound. In this case, it's 0. So that's that. If you were told, however, if you were told how much water left it between, let's say, like t equals 10 and t equals 45, this would be your new lower bound. And I'll just have to do that here. So we take back this function. So it's going to be the upper bound, which is going to be this here, 5 times 45 plus 45 squared over 2 minus 5 times 10 plus 10 squared over 3. And this here, we already did it. It's going to be 1,237.5 gallons. And this here is going to be, oh, this is, I can just do myself, 50 plus 100 divided by 2. So that's going to be 150 plus 100 divided by, it's going to be 100. So 100. So this is going to be 1,237.5 gallons minus 100 gallons, which is going to come out to a total of 1,137.5 gallons. And this is at, if you were told to evaluate it from t equals 10 into t equals 45. In the actual question, you were asked in total 45 minutes. Maybe I should have specified after the start, because you could just move the 45 around if you wanted to technically. But let's pretend it said here after, since the start. That's how you would evaluate it. You go back to FTC here. Did I already pass it? I think I did. Yeah, here. And to recall, can you guys see it? There. And we are taking the indefinite integral of the function. I guess this is in my words. We're taking the indefinite integral. We're leaving out the c, and we're going to evaluate that then at the upper and lower bound. That's going to give us the net change. And just to recap, the net change is the displacement, which is the change of from where you started to where you ended. So if I go from Gainesville to New York or something, my net change is going to be like 1,000 miles. If I come back to Gainesville, my net change is going to be 0. And this formula will give you the net change. And I think that's it. And I think this is a great way for understanding it a little bit more, because this way is a little bit more it's more technical, and I think real world examples are really helpful. And so I think this is a more real world example where you have velocity, and you take the integral, you get the position. Where you take the derivative of this, you get the velocity, and you can also get the acceleration. And I think that's it.
Yeah, this is good. And there are just a few little details that I want to wrap up and a few questions that showed up in chat. But I think the bulk of this is done a really good job of presenting the things that people need to have kind of clear in their minds. There are just a handful of technical elements that I want to point out a little bit. And some of them you nailed, like when we talked about the units. Let me see. I think I'm going to have to steal the screen share back here. So let me do this. So
I'll just put it back up here in case anyone moves it.
Yeah, so if you want to take a look, if you still need to write down what Daniel has there, you can double click on his window and it will show up. I'm just kind of keeping a little tally of questions that came up in the chat that I want to address really quickly. So first, the difference between definite versus indefinite integrals. Certainly, this is something we could deduce from the last couple lectures, but I think it's worthwhile to be as clear as possible. So a definite integral, and Daniel did say this, this is the integral from a to b of f of x dx, or whatever your variable is, but integral from a to b of some function. And this will always come out to a number, specifically the signed area, bounded by f of x from x equals a to x equals b. And we all know that the indefinite integral, the way I've always liked to say this is that it's really just, also first the notation, right? Integral f of x dx. And we do want to write the dx at the end here. The integral without bounds is called the indefinite integral. And really, this is just a notation for the most general antiderivative. Of little f. So the reason we introduced this notation instead of the notation that Talia used in 4.9 is because we discovered through the fundamental theorem of calculus that the definite integral is evaluated by finding an antiderivative and then plugging in these numbers. Well, if you want to discuss the antiderivative without plugging in numbers, just the thing that we've been calling capital F, wouldn't it be nice if the notations kind of matched up? So antiderivative with some numbers plugged in, the antiderivative without some numbers plugged in, well, it's just the same symbol without those numbers, a and b. And these, this is an infinite family of functions. Or if you just want to say it's a function, that's okay. But with that plus c, remember, that's all the vertical translates, right? So it's you have kind of your core antiderivative, the thing you get from your antiderivative rules, and then you add on that plus c. So it's a function plus c, which is an infinite family of functions, or all the vertical translates of the antiderivative of little f. Let's see, there are one or two other things that I wanted to mention here. Brain, come on. So the net change theorem that says that if capital F of x is an antiderivative for little f of x, then the net change in capital F from x equals a to x equals b, which remember by definition is f of b minus f of a. From pre-calculus, that's what net change is. It's how much has the output from your function changed as the input goes from a to b, is the definite integral from a to b of little f of x dx. And this is an immediate consequence of FTC2, right? FTC2 says that the integral from a to b of little f is big F of b minus big F of a. It's not, there's no heavy mathematics going on here, but the interpretation is what matters. So the kind of examples that we looked at there are good. Let me just recap sort of the thing. So like the first and maybe most natural one is if v of t is the velocity of a particle of an object in one-dimensional motion, then the integral of v of t from a to b dt, this would be the position function x of b minus x of a, because the position function x is the antiderivative of the velocity. And this is how far you started or how far, let's say like this, how far you ended up from where you started. So this is the classic example of the net change theorem. And this thing over here, we're very tempted to call distance. But the one subtlety I wanted to discuss is that this isn't necessarily distance. Like Daniel said, if you drive from Gainesville down to Orlando and then back to Gainesville, your net change is 0. You end up at the same place you started. But you certainly didn't go 0 distance. You've gone something like 200 miles. So there's this thing which is called displacement. That's the term for how far you ended up from where you started. It's your displacement. And distance traveled is found by integrating the absolute value of your velocity function from A to B. This is the distance traveled. And sometimes they are the same thing. Sometimes these are the exact same thing, but they're not always the exact same thing. You can ask yourself, under what conditions is this integral equal to this integral? And I think it's pretty clear that the necessary and sufficient condition is that the function v of t be the same as the absolute value of v of t, which means v of t needs to be positive. And thankfully, that quadratic that Daniel used there, because all the terms were positive, is a positive function. These are the same, provided v of t is positive on the interval AB. But that need not be the case. So I would like to take a quick look at one example where we contrast these, where we find our displacement and our distance traveled. And in particular, I want to show you how to do an integral of an absolute value function like this. That's a little tricky on its own. One other thing that was mentioned in chat, like when do we use a plus c? Plus c's show up only here with indefinite integrals, right? Because that most general antiderivative always has a plus c. You don't need a plus c when you find your antiderivative here, but you can use one, right? Like Daniel wrote down the plus c when we did the integral of the velocity function, and that's okay. Because remember, FTC2 says if capital F is any antiderivative of little f, then the integral from a to b of little f is big F of b minus big F of a. So you could use that particular guy with a plus c, but you need not. So it's up to us. Generally, when we do a definite integral, we leave off the plus c just so we don't have to write as much, because it will always cancel when you evaluate. And Yiping's comment in the chat there is exactly correct. If you're trying to find the distance traveled, if you're trying to evaluate the integral of an absolute value of a function, the game is to alter that original function so that the area underneath its curve is measured as positive all the time. So I do have an example in your textbook. Let me grab that. It's not a bad one. It's not terribly hard. It's towards the end here. And then I also want to provide you with that table before we go. Here we go. So where's my velocity function? Oh, this is, here we go. So v of t, s, by the way, is the same as x. Different books and authors use different notation, s for position or x for position. So v of t is t squared minus t minus 6. And I want to find the displacement and distance traveled from 1 to 4. So I'm just going to copy this down. T squared. 1 less than or equal to 2 less than or equal to 4. And this is going to be in meters per second. Okay. So here we go. I have some object moving along a straight line and his velocity is given by v of t equals t squared minus t minus 6. I want to find the displacement, which is how far that object ends up from where it started, and the distance traveled from time t equals 1 to time t equals 4. And these are measured in seconds. The displacement is the easier one. That would be the integral from 1 to 4 of v of t dt, which is the integral from 1 to 4 of, I'm going to be very picky with my notation here. I know that writing the differential at the end is something that's easy to get out of the habit of doing. I will ask that you please do always write the dt or the dx at the end here. You can think of it as telling us what variable we're integrating with respect to. So just like you can differentiate with respect to x, you can differentiate with respect to t, you can differentiate with respect to y, you can integrate with respect to different variables also. And this guy at the end tells us what we're considering as the variable for the calculus operation. The other little notation point I'm going to make is that when you have an integral with multiple terms inside, separated by addition or subtraction, it's very nice to put that whole thing in parentheses, put the integrand in parentheses. So we will apply our power rule to each of these three pieces. T squared has antiderivative t cubed over 3, minus t has antiderivative t squared over 2, minus 6 has antiderivative 6t. And I'll evaluate this from 1 to 4. And that's going to give me 4 cubed over 3 minus 4 squared over 2 minus 6 times 4 when I plug in t equals 4. And then I subtract what I get when I plug in my lower bound, which is 1 cubed over 3, or 1/3, minus 1 squared over 2, or 1/2, minus 6 times 1. And we can clean this up as much as we want. That's 64 over 3, minus 16 over 2 is 8, minus 6 times 4 is 24, minus 1/3 plus 1/2 plus 6. If I put the integer pieces together here, I've got minus 8, minus 24 is minus 32. Minus 32 plus 6 is minus 26, right? So I've got 64 thirds minus 1/3 plus 1/2 minus 26. And then each of these I can combine into a single fraction if I want to. 3, this already has the denominator 3, so maybe we'll say this is 63 thirds plus 1/2 minus 26. 63 is that is divisible by 3, right? Yeah, this is an integer. So what is 63 divided by 3? It's 21. So that's 21 plus 1/2 minus 26. And then 21 minus 26 is -5 plus 1/2. And those we can put into a, well, I'll just call this negative 4.5. We'll use some decimals because we're talking physics stuff here, right? And this would be measured in meters. So the fact that my displacement is negative tells me that I've gone further backwards than forwards. I ended up 4.5 meters behind where I started. Any questions on this little evaluation here, on any part of the displacement calculation? Okay, and then for the distance calculation, like Yiping said, we need to make the velocity function always positive. So let me sketch the graph of this velocity function really quickly. T squared minus t minus 6. I think that factors, right? That's t minus 3 times t plus 2. So this is a quadratic. The lead coefficient is positive. And we have roots at -2 and +3. The y-intercept is -6. So let's see here. My vertex would have to be halfway in between those guys. So the curve is looking something like this. Modulo my bad art. Our graph of v of t is something like this. And what we want to do is find the distance traveled from time t equals 1 to t equals 4. So drawing the picture, you can see why that first integral came out negative, right? This function, well, not the pen, please, the pencil. This function spends a lot more time down here than he did up here, at least on the interval 1 to 4. So
how do you know the vertex is at axis equal to 1?
I don't, I'm approximating. But if you want to, you know, it's exactly halfway between -2 and -2 and +3. So it's actually at, I think 5 halves, right? Is that right? Yeah. Yeah. So the vertex isn't going to be right here. It would be actually a little bit to the right of this. So the vertex for a quadratic is always halfway between the roots, right? So the halfway point between -2 and +3, let's see, the gap here would be 2, the gap here would be 3. So this isn't quite right. We need to go half a little further. So the vertex is a little bit to the right of that.
So is it 3 minus 2? So it's 3 plus 2 is equal to 5. 5 halfway is 2.5.
Right. Yeah. So my vertex is actually like right here, a little bit to the right. But it's a rough picture. It doesn't have to be perfect. The important thing is that we know where the velocity function goes from being negative to being positive. And that's right here at 3. So if I call this first area A1, and I call this second area A2, the displacement, which was the integral from 1 to 4 of v of t dt, that was -A1 plus A2, right? This area is measured as negative because it's beneath the t-axis. My distance traveled which is the integral from 1 to 4 of the absolute value of v of t dt, this would be A1 plus A2. So we can find this area, make it positive, and add it to this area. So to do the distance calculation, first I'll do the integral from 1 to 3 of v of t dt. I fully expect this to come out negative, right? Because this area here is all under the t-axis. That's the integral from 1 to 3 of t squared minus t minus 6 dt. And the antiderivative is still the same thing we did before, t cubed over 3, all coming from the power rule, minus t squared over 2 minus 6t, this time evaluated from 1 to 3. And that guy is going to be 3 cubed over 3, which is 3 squared. I'll write it 3 cubed over 3 minus 3 squared over 2 minus 6 times 3 minus 1/3 minus 1/2 minus 6. And if you'll allow, I will just go ahead and use a calculator for this so I don't burn too much time. So 3 cubed over 3 is 9 minus 9/2 minus 18. And then we have minus 1/3 plus 1/2 plus 6. So this is -7 and 1/3, or -24/3, 22/3, sorry. And so this would be like part 1. And part 2, I do the integral from 3 to 4 of v of t dt, which is the integral from 3 to 4 of t squared minus t minus 6 dt, same antiderivative, t cubed over 3 minus t squared over 2 minus 6t, this time evaluated from 3 to 4, which is 4 cubed over 3 minus 4 squared over 2 minus 6 times 4 minus 3 cubed over 3 minus 3 squared over 2 minus 6 times 3. And again, if you don't mind, I will yield to a calculator here just so we don't burn too much time. And we have minus 9 minus 9/2, sorry, plus 9/2, plus 9/2 plus 18, which has a ratio is 17/6. Okay. So calculations so far. The integral from 1 to 3 of v of t is computing this. So if I'm just looking for the area, A1, that would be positive 22 over 3. And A2 is 17 over 6. Which means that my distance traveled, right? I just fixed this to make it positive. So the distance would be A1 plus A2, which is 22/3 plus 17/6. That's 44 plus 17/6, so 54 61/6. And 61 is definitely not divisible by 6. So I'll just leave it as this. I guess we can ask for a decimal. And physics stuff likes decimals. About 10.16 repeating meters. All right. So the displacement was negative, but the distance traveled was positive. And that's because we spent more time going backwards than we did going forwards, right? My velocity is negative everywhere through here, which means I'm heading in the backwards direction. And then my velocity is positive only from 3 to 4, which means I'm heading in the forwards direction. There are other ways to do these sort of calculations, right? There are other ways to integrate the absolute value of a function. But I think this is the simplest way, right? So if you're struggling or confused by these sort of things, I suggest that you draw the graph, gotta draw the graph, and then just recognize that any portion of that area that is going to be measured as negative by the displacement integral needs to be fixed to become positive by the distance integral. What else did we want to say? think that's mostly it. In general, the integral of a rate of change is the change itself. Let me just end by saying this. So your textbook has a number of other good examples here. If you have water flowing in or out of a tank, and V of t, capital V of t, is the volume in that tank at time t, then the derivative V primed is the rate of change, right? How fast water is flowing into or out of the tank. So if you integrate that rate of change, you will get the net change. Other ones in here that I kind of find interesting, density, right? If you integrate the density, then you can get the mass. And if you integrate the marginal cost, you can get the change in cost. So I would suggest reading the textbook to take a look at some of the application examples and see if you are comfortable with the units. What else? Oh yeah, there's a table in here. That's the other thing I wanted to mention. So there are a few examples like these that I think are worth taking a look at. Those are both definite integrals, but indefinite integral examples, definitely worth taking a look at. But all of the antiderivative rules can be written really nicely in terms of the indefinite integral. So I'll just, in parting, say this. What page are we on? 403. So it's the same table that I wrote down for you at the end of Talia's lecture, all of the antiderivative rules. They're just rewritten in this nice notation of the indefinite integral. And you do need to commit those to memory. These are things that you do need to remember. So constants pop out. You can split up over addition. You have your power rule. You have the integral of 1 over x being the natural log. And all of those basic rules, right? All of those basic antiderivative rules. You do need to know these things, right? So like on an exam, I'm going to be assuming that you remember all of these rules, perhaps with the except, I mean, the hyperbolic sine and cosine is fine too. Yeah, you need to know these. What else? There's one flavor of problem that I think you should practice that we didn't get, I think maybe quite enough work with today. I don't see them here actually, which is really disappointing. So I'll make sure to drop them in your homework. But it's the same sort of stuff that we did in the antiderivative section, where you want to split up functions as much as possible. Yeah, so Sarah mentions in chat, since we already know all of the derivative versions of these rules, we're really not memorizing something new. You're really just learning the new notation. So like, you know, the derivative of cotangent is negative cosecant squared. And you can deduce from that that the integral of cosecant squared is negative cotangent. That's fine. And that's, I think, how most people do it at first. Okay. Any questions for me before I let you guys go?
What will you teach? Which chapter will you teach next Monday?
Next is 5.5, which is on the substitution rule, U substitution.
I see your syllabus is 4.9 or something. It's some chapter is before. So will you teach those two?
We are going to go back and revisit some things, some topics from earlier. Let me see. So I am going to talk a bit about differentials again, because we're going to need that for 5.5. The mean value theorem for integrals, we're going to talk about that a little bit.
Which chapter?
Stuff is sort of stuff that we've already covered. So we're not going to be going back to other applications. We talked about that back when we were talking about the derivative. But if you go back to section, what was it? It's not something you need to stress about. But if you go back to section, where was it? I don't see it here. Maybe it was here. Linear approximations and differentials. So we're going to go back and revisit section 3.10 a little bit, because I just want to remind you what a differential is, because we will need those. So remember this stuff from the linear approximation section, calculating differentials. We will need these to do substitution. And that's why I put that in the syllabus there. The other thing that we're going to go back and talk about a little bit more now, I'm going to revisit the mean value theorem, because there's a version of this for integrals.
So before you teach 5.5, you will teach 3.10 and the 4.2.
Yeah, and those are both things that we've already talked about, but we will talk about them a little bit more before I teach 5.5. So on Monday, I'm going to go back and remind you how to calculate a differential. I'm going to remind you what the mean value theorem says, and then I will show you the mean value theorem for integrals, which is a very neat thing, and I will show you the substitution rule. The vast majority of the time will be on 5.5. Basically, those little things will just be quick recaps, right? Differentials were defined in 3.10. So I'm going to go back to 3.10 to show you a little bit there. And then the mean value theorem for integrals is a nice way to kind of interpret the mean value theorem that we learned about back in chapter 3, now that we know about definite integrals. So it's not, think of next Monday as being substitution. Really just substitution, but I will be reminding you of some of these old things and helping you see them in light of the new things.
What is this chapter? I saw it's chapter 6.
Yeah, this is technically in 6.1.
Okay.
But don't worry, we're not going to cover any of the other material from 6.1. I'm just going to show you these two different versions of the mean value theorem. So think of Monday as being just 5.5. 5.5 with a little bit of seasoning.
Okay.
And we will review the mean value theorem. Differentials. So kind of think of these topics as review, and then really we'll be doing substitution, which is 5.5. And then I saw there was one other comment there. Yeah, I think we are getting close to Sarah's student teaching day, which is 6.1. I think now would be a good time to start preparing. So 5.5 we'll spend at least 2 days on, because it is a tricky section. It's one of those sticking sections, place where you really need to get this in order to do well in Calc 2. And because we're going to review those other things before diving into 5.5, I think probably we'll do 5.5 both Monday and Wednesday. But then Friday of next week is most likely going to be the appropriate place for areas between curves. Yeah. Oh, well, Friday of next week, no, you don't have class, Thanksgiving. So that would be Monday the following week, right? Yeah, so I will do 5.5 Monday and Wednesday of next week with those review sections tucked in. And then Monday the following week, we can do 6.1. And then Wednesday, we can review for the exam 3. And then exam 3 will be on the last day of class, Friday, December 3rd.
When is the holidays?
The college is closed Thursday and Friday of next week, the 25th and the 26th.
Okay.
Yes, Sarah, you have everything that you'll need to understand 6.1. It's just definite integrals. That's the only background you need. And then they use some geometry, thinking about definite integrals geometrically in order to come up with areas between curves. But as of last time, we have everything you need for 6.1. Alrighty, any other questions from you guys before we get moving? Sounds good. All right, then I'm going to go ahead and end the meeting here. Thank you, Daniel, so much. That was really nice. It's brave to do a live lecture, and I think you did a good job. I genuinely appreciate taking the time and having the bravery to do that stuff live so that people can think along with you. I think that really is a valuable thing. And thank you to everybody else for attending and paying attention, engaging so nicely with the material. If you do need to talk to me, of course, office hours, Canvas messages, emails, you know the deal. Otherwise, I will see you guys next Monday. Take care.